In addition to working with this organization, I also work with SBS. And we've been hampered by the pandemic, but our sort of primary objective is science outreach. So, where do we go?
You go to like high schools and I believe middle schools as well.
Actually, we've been to elementary schools too.
Oh, elementary school.
And what do we do?
You make a lot of there are physics demonstrations. Like for example, you might take a balloon and pop it with a.
Oh, you're supposed to say it the way most people say, oh man, they smash stuff up and
that's-
things and like, make things shatter that aren't supposed to
I've
shatter.
heard the cooler stuff that came to my house.
So, when you're trying to convince somebody, when you're trying to do outreach with science, and I don't know how outreach works in other disciplines, but you got to do a couple of things. First, it's interesting. Second, you can do it if you want to. There's nothing magic about it except lots and lots and lots of hard work, right? So the best we can hope to do in an event is kind of convince them it's interesting. And one of the best ways to do that is, my wife also teaches science, and it's like her favorite quote in the world, it's on her door. It's not what you don't know that gets you into trouble, it's just what you know for certain that just isn't so. So, wheel on a rope. Now this thing's really heavily weighted, right? This strip here weighs a lot. So, I hold it by the rope, what's gonna happen?
It's gonna swing out.
What do you mean? Where's the wood bit gonna be?
Down.
Down. Yeah, okay, no problem. Alex, come here.
Alright.
Get that sucker spinning. No, no, no.
Oh, wait.
Grab this.
This.
Like fast, like real fast. Like, what are you doing? I ain't got all day. 8 times that fast. Okay. Now what am I gonna do? Here, hold it for me for a second. Like that string, right? If I hold it up by the string, what's gonna happen? Go ahead. You got an answer for me? The brown bit ain't pointing down.
The circular motion causes it to spin around the circle.
Well, this motion is just what's called a procession. It's a minor effect. The main thing is how come that brown handle can't point down? Now, it's spinning.
Alright, we're all weak, so.
Toughen up, man.
I'm not sure, but I have one answer.
Okay. That's going to be the name that people give what they call a pseudo-force. But that's just a correction for the fact that you're in an accelerating frame. The actual dominant effect here is the conservation of angular momentum. This thing right now is spinning about an axis that points along the ground, right? In order to point down, it wouldn't have any motion around that direction. So it would have to get some. It doesn't have any, so it can't. Right? Now, we're going to give you one more chance to prove your strength. Ready? Grab that wood handle. Make the gray handle point up. Go ahead.
Like both my hands?
Yeah?
That's one.
How hard was that?
Pretty difficult.
Pretty hard?
Yeah, pretty hard.
What are you talking about, man? Conservation of angular momentum. It's a basic rule, but you can get kids intrigued by showing them something that behaves in a way they wouldn't expect. Kind of a weird looking cylinder ball thing, right? Put it on the slope. What's it gonna do?
Roll down the slope.
Let it go right here, it's gonna roll down the slope, yeah? Let's tilt it up on that side, yeah?
Yeah. Oh.
She's full on, dude's a magician, he's doing some trick.
Oh, no, I just.
No trick,
I'm
everything is
just curious.
exactly as it appears.
I'm trying to contemplate.
And if you looked at it carefully, you would understand exactly why. What did you say it was supposed to do?
Go down the slope.
And that's exactly what it did.
Okay.
This line points down this way, but this thing doesn't care about that line. This thing's center of mass is trying to get lower. By going out to where it's wider, it can go further out on the axis. Center of mass is lower here than here, even though the thing is turning this way. Right? All right, so that's sort of the spirit of the thing. And trying to pick a couple to actually show you something, I figured I'd start with sound, right? And you know something about sound. First, let's start. Oh, just gotta grab that. You on? What do you know about it? Now you're getting on my turf. My research is ocean acoustics. It's a wave. Okay, great. What could be different amongst different waves? Amplitude, frequency, and wavelength. So amplitude would be a kind of intensity, right? Strength. Amplitude and, or excuse me, wavelength and frequency. Inversely proportional, yeah, but it's actually, it's much more natural than that. You're thinking of that as like, somebody said that in a math thing, and like,
I'm math major, so.
oh, great. Well, there's a reason why it has to be that way. If you take the wavelength and multiply it times the frequency, that's the speed that the wave is traveling, right? Think about it. If you took a picture of a wave going by, you'd see like a sine wave looking thingy with some wavelength, right? But if somebody else's job was not to take pictures, but to watch the wave go by, and they drew it as a function of time, they would see kind of a sine wavy thing too, right? And they would say the time it took, it was a period. You with your camera would say the space it took was a wavelength. But the only way that it got through a full oscillation for the guy who's sitting still is to have scooted over a wavelength. So every wave travels a wavelength in a period. Period is just the inverse of frequency, right? So yes, they're different measurements, but they're related, and you can characterize waves with either one, right? But the product of those two has got to be the speed, and that's kind of wave and what it's traveling through, right? All right, so my point was supposed to be, before my computer took a crap on me, that wavelength times frequency is supposed to be the speed of the wave, right? What do you know about different tones?
They have different frequencies.
Okay, so
What kind of frequency is this?
So low.
lower frequency, right? And then, you know, opera singers, high frequency, right? But if wavelength times frequency is supposed to be a constant, that would mean that low frequency ought to be a bigger wavelength, right? Well, I can't sing for anything. So, tuning forks, right? Get nice clean. Yeah? And this one's at 256, which 256 hertz, which acoustics people will call C. Musicians will argue with you, no, it's supposed to be 258 or whatever. 256 is a power of 2. Therefore, we're going with that one. But you'll notice that this one makes a certain sound, and that has a wavelength that's has a relationship to how long that fork is, right? So, this one's tone ought to be, because it's a shorter wavelength, right? Okay. So, you can tell big wavelength, low frequency, low wavelength, high frequency. Yeah? I shouldn't do that at the heart. It's not very accurate. All right, well, you know another wave, yes? We've come to the audience participation part of the proceedings. Are you ready for this? Well, everybody's in on this. Silly
I'm
little
always that person.
rave
Somebody
glasses.
asks the volunteers, plus you want to run.
Who saw me in heaven? Seeing little rainbows? Yeah? From which you should be able to figure out two things. What do you think? White light's got all the colors in it, right? Otherwise, how would you separate out the different colors if they weren't there in the first place? Yeah?
Yeah.
Now, it turns out fluorescents are actually kind of crappy white lights. Their frequency distribution isn't very flat, but it's got different colors in it. I ain't an interior designer, I don't care. Right? But you're missing an even more basic point. These things separate the different colors of light. Right?
Essentially,
All they are, and these are super cheap ones. Actually, his aren't, yours are. It's just little sheets of plastic, and they just take something and scratch it every fraction of a millimeter, right? And that way, light that goes through there is just randomly scattered. But if you manage to get between the scratches, you get through clean, right? So if you have a couple slits and you're not dead center, but off over here a little bit, right? The colors that constructively interfere over there, it'll be a function of their wavelength. So maybe blue interferes constructively right here, red would be over there. The fact that those are different and depend on the wavelength means you'll see the different colors separated out by constructive interference. Yeah? All right. What do you know about a laser? I bet you I can shoot right in this camera. Fry every photocell in the thing. You can take the things off. You guys look like you're at a Devo concert. What do you know about lasers? What do you know about it? Nothing? Nothing. Well, how white does that look? Not
couple
even slightly.
millimeters.
What's that?
Couple millimeters.
No, how white?
White.
Like,
Okay.
does it
Not
look like
white.
that?
No, it does not look white.
That looks like it's just red. Yeah? In fact, we can readily confirm. Here, those are better. It doesn't make rainbows. Yeah? So, that means, unlike the white light, this doesn't have all the colors in it. Right? And in fact, what a laser is exploiting the fact that not only is light a wave, it's also a particle. There are atoms in this thing where the energy amount associated with a particular kind of atomic change, whether it gets a little more excited or drops down to a lower energy level, has got a really specific energy amount, right? And so if it gets excited and drops down, it can only emit that much energy, right? And so it will or it won't emit a single particle of light. And there's a whole bunch of atoms. And this thing is carefully built so that all of those atoms, when they emit light, they're like trapped in a little chamber. And having light of a certain frequency around things that are thinking about emitting light of that frequency makes it more likely that they will. So the first guy emits, that makes the second guy more likely to emit. And the first and second guy make the third guy much more likely to emit. And the 800,000th guy is like, yeah, he's definitely gonna emit. Right? So it's using a battery to excite all the atoms, but they're all dropping in a very organized way with all of their light emissions being the same way, exactly the same frequency. That's what you see.
Is it
And
controlled
it ain't
by
got a bunch of colors in it. No, go ahead.
Is it controlled by the amount of voltage it gets from there?
The electrical part is called pumping, and it's not really that, it's not that delicate. Just start kicking the atoms and you'll get excited, right? It's the emission part of it that's really, once they get started emitting a certain way, all the other atoms are gonna say, okay, our light's going that way and it's exactly 632 nanometers wavelength, right? So, very specific color. But, this is green? No, that ain't green. This thing's a light. You can see what turns out to be a pretty narrow slice of the different wavelengths of light. We call those the visible. And those are wavelengths of something like 400 to 700 nanometers. Different wavelengths of light. Sound, they were different tones. Different wavelengths of light are different colors. Yeah? So if you can see about 400 to 700 nanometers, what's 400?
Red.
Other way around.
Violet, VIVGYOR, so R is on the far end.
Red is the long wavelength,
So the other end.
so that would be the low frequency, right? And it turns out that that means purple light, particle for particle, is more energetic than red light. So this, right, and it's very rough and it depends on who you're talking about, but you can see about 400 to 700. This is about 630, 650. It's not actually a 632, which would be the box every teaching lab in the world has in it, 632.8. This isn't that, so it's off that a little, something like 650. Point is, it's clearly red, but it's kind of an ordinary red. This, it turns out, is like right on the edge of what you can see. And so at least with me, it messes with my head. Your eye keeps going, can I see it? Can I not see it?
Yeah, it feels a little weird like that.
It just feels odd, right?
Yeah.
You're like right on the edge of whether you can see it. So are you supposed to just believe me? The red wavelength is the long one and purple is short? You're supposed to be both skeptics and interested in science, right? You're supposed to say to anyone in the world, prove it, man. Okay. Which dots are further apart?
Red dots.
Right? So therefore purple is the short. And if you got real picky about that, you can convince yourself the ratio is about 4 to 6.5. Yeah? Makes sense. Plus it looks great. I can do it with Christmas colors too. But that's not that fun because the wavelength discrepancy isn't all that great. But you can tell red is longer than green. It's hard to, it's not that dramatic a difference, but red's longer than green. Yeah? All right, so that's wavelength. But light is a different kind of wave than sound. Sound is what we call a longitudinal wave. You know what that means?
I should, but I don't.
I'm not telling you should. I'm always just kind of curious what people do.
Oh, I'm in marine science, I probably should.
Well, eventually, and in fact, I've argued I should be teaching you guys in acoustics. Longitude, eventually you're going to have to at least talk to somebody who uses sound, right? Even if it's just internal instrument communication, top of the rig to the bottom. Probably to an acoustic or from a cable, by the way. Point being, sound comes out of my mouth, it's pushing on the air, right? So the air gets kind of squeezed and released. The little air molecules aren't making the trip, but the pattern of compression is traveling outward. But when those air molecules do move, when I'm yelling at it for being a smug little, they're going this way, along the direction of travel, right? Light is electromagnetic. If light is traveling this way, the electric field has to be perpendicular to that, right? And further, the magnetic field has got to be perpendicular both to the way it's going and to the electric field direction. So if the light was going this way, the electric field was up, B would have to be this way. So B to my right for E up and the wave going out, right? in some way it's maximally transverse, right? And again, blah, 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 I don't believe you, old man. All these things is a kind of really long polymer plastic, right? You look at the light through it, what do you think? It's a little darker, yeah.
Yeah.
Only some of the light's getting through. And plus it's filthy, God damn it. Right, that's all you really know, yeah? How about if I put another one? What an enormous difference that made, right? Looks totally different than just one. No, that's not. Yeah? Still just like, well, not all of it gets through. You say two of them are exactly the same as one, huh? Because these things are long chain, they only let light with their electric fields in a certain direction through. If your light trying to get through this thing, only if your electric field is this way will you get through. Any light who has their electric field this way, not making it. Yeah? So if I do that twice, who cares? Because if you got through the first one, the second one's no challenge, right? But if they're crossed, you can't get anything through at all. Yeah? So there's no way to get light through these two, right? Yeah? Don't ever tell a scientist you can't do something. Never, never, never. I will figure it out. Tell me I can't get light through that thing.
You can.
See it?
Yeah.
So what's going on?
Does it bend the light so that it can break through? Or bend is the wrong word, but it goes
You're
through.
on the right track.
It goes through one way, so perpendicular.
The way to think of it, and you actually have the language for this, is taking a component. If I hold this up, the incoming light's got all kind of random. It can be anything perpendicular as long as it's going through the sheet. It can be any of these directions, right? So those parts of the light whose electric field is a little off this thing's axis get most of their light energy through, but not all of it. Take a component, right? So if I then take this component, well, you're getting it a little darker. But by putting a halfway axis in the middle, I've made it so that you take a component twice and manage to get through. Not a lot, but some. If you take light that's this way and take its component along this axis, no good, right? But if you take light that's this way, take its component along that axis, you get a little something. And then take the component of that along up and get a little something. So that's what this is doing. You don't gotta raise your hand.
When you say perpendicular, it doesn't have to be like perpendicular. It can be its nearest some threshold. So it's just like a threshold, right? It has some threshold. Okay.
Right? So it'll be whatever, this, because the incoming light is random, lets a certain fraction through, right? It's only the relative between these two. But if they're aligned, then the second one's irrelevant. But if they're perpendicular, you can't get through. So it's continuous.
So what that did was just made it relative.
So that rather than taking the component of this along a perpendicular direction, you took the component of this along this way, and then the component of this along this way. And neither of those is strictly zero. Small, but not zero. Yeah? Makes sense. You understand light? Light experts now?
Far from it.
We like it.
Yeah.
What's that?
Yeah, red balloon.
You say red?
I mean, that's my.
Well, I'm not quibbling with your choice of colors. And in fact, she was pointing out how there's, the visible goes from violet to red.
Yeah.
Physicists, that's way too fancy for us. It's blue. And so we'll say the short wavelength high frequency end is blue. The long wavelength low frequency end is red. So we end up saying things that sound insane, but make perfect sense in physics. Violet is bluer than blue. Sounds like a crazy person. And incidentally, the shift of frequencies depending on whether a source is heading toward you or receding. If you ever flip by those annoying car races on TV, you know, all the time, right? When it's approaching you, it's higher pitch. When it's going away, it's lower pitch. It's called the Doppler effect, right? If you go look out in the sky, everything that isn't right in our neighborhood in space is red shifted, which means it's moving away from us. That by itself is completely conclusive evidence of the Big Bang.
The Andromeda blue shifting.
What's that?
So the Andromeda galaxy is blue shifting.
Yeah, it's like 4.5 light years away, man.
Yeah.
That's the neighbors.
Oh yeah, that's pretty relatively close.
It's extremely close.
Yeah.
And that's, you know, anytime you're a participant in the Milky Way, your relative motion to us is going to be dominated by spiral arm positioning, galactic rotation, right? I mean, anybody out, everybody else is moving away from us. Outside of local structures. How can everybody be moving away from us? Because we all emerge from the spot. Right? I think of that as a final, utterly decisive, there was a Big Bang. But it's not even close to the best piece of evidence, which is, if you go look at a dark patch of sky, it's little tiny radiation, a microwave background. Its character, its nature is such that if you take the prediction of the Big Bang Theory that the universe was once compact enough that everybody was in thermal equilibrium with each other, and then went right? The radiation you would predict, as compared to the radiation we see, theoretical prediction and the data points uncertainty is so small, it's typically on a normal picture less than a pixel. It's amongst the most accurate measurements humans have made. Okay, that was a long, twisted, winding road of an aside. It's a damn red balloon. This is an obnoxiously red shirt. What do you mean by that?
Well, it just reflects, only reflects red light.
There it is, right? Why is this thing red?
Because it absorbs all other wavelengths but red.
Or at least better absorbs.
Better.
It turns out you don't need all that much of a statistical tilt. If you ever watch like a sports event on TV where the home team, their color is red, if 1 in every 4 people is wearing red and everybody else is random, the crowd looks totally red, right? So it's not necessarily that it has to perfectly emit or perfectly reflect the reds and absolutely absorb everything else. It's just better at absorbing other stuff and reflecting red, right? So, this would be green. I'm going to take this green. All right, these labels say that those two are the same color. Bunch of liars. Those are my two colors. Anyway. Let's see. Give me a green. Here's a green. That doesn't want to be green. I just had a green, I know I did. Yeah, I just showed them all. There it is. Green laser. Green balloon. It's gonna happen. He's already gearing up. I heard these physicists blow stuff up. No.
Logically, it should not absorb green. That's what.
Okay, so what is absorbing the green? How's that relevant?
We shouldn't see, if it was absorbing green, then we wouldn't see green.
Okay, so what's it gonna do when I shine a laser on?
It
Pass
should.
through. Some of it clearly will. In
Yeah,
fact, it looks pretty cool.
This one's not strong enough to really do.
Will it reflect off it?
And decide if I Did it pass through or reflect?
Well, some's gonna pass through, because you can kind of see through the balloon, right? But the point is, it's not necessarily absorbing all that much of it. Right? And in fact, remember how I said that if you have some light at a particular state, how nearby light wanted to do exactly the same thing? You look really close, see little tiny speckles?
Yeah.
That's where locally some nearby light has decided, we're in pretty much the same state, and your presence makes me want to be in exactly your state. So it's called laser speckle. Yeah,
That's super cool.
thing didn't pop. What does that mean? That rather than absorbing the light, taking that energy, using it as heat to make the molecules oscillate, absorbing that heat, and eventually blowing up, you're reflected, at least enough of it. What do you think?
Gonna fall?
Yeah, for sure.
I don't know. Huh.
Oh. I guess it,
Huh. Doesn't seem to be working. Anybody got any thoughts?
I guess you need one, I guess you need a different frequency.
Say it again, much louder.
So I guess you need a different frequency, that one's a little,
Well, that could certainly be part of it, that even though it's really good at green, reflecting green, that red is kind of, it does an okay job of reflecting it. That's one theory. Let's test it. I have a good sharpie somewhere. Hopefully this will be good enough. Maybe it's just that even at this red, it's still managing to reflect a decent amount of it.
yeah.
What do I do about that?
Absorb the vast
Should
majority of it.
absorb.
If I make it black, that's supposed to absorb everything, right? Let's see here. Is the ink dry enough that I won't just boil off the ink? You guys thought I was crazy. Which is true and irrelevant.
We did, but for not the same reason.
Well, I guess now that we've descended into balloon torture, clearly why don't I just show you? I think these nails are very sharp. They are. I just failed to settle this thing down because it was sitting on its head.
You gotta destroy something.
I'm gonna shove this guy between two boards. What do you think? It's gonna be fine? Why?
I tell you it might be funny.
Okay.
I'm from India, I've seen a lot of swans.
Yeah,
do
we've
the
got
nail
the-
bed thing.
We've got the bed of nails
Bed
over on the left,
thing.
yeah. Human size, yeah.
I think it's
And the first guy who got it.
distribution of, I'm sorry.
First guy who got on it took some nerve. Everybody after that is like, oh yeah, of course it would.
It's equivalent distribution of, I mean, I don't have exact words, but equivalent distribution of force.
How do you stab through the skin of a balloon? By making it so that one spot has enough pressure, right? To break through the skin and let the higher pressure air on the inside out and equalize with the surrounding air. Or if you've got a Swami who's pretending like this is some illustration of great skill or enlightenment or something, lay on the
You call them
lots of
what?
nails. Anybody can do it. It's nothing to it. But it's surprising how much you can do as long as you spread it out, so that because you're doing 50 points, you gotta push 50 times as harder to get any one to reach the threshold of top of your skin. Yeah?
Yeah.
So, they're starting to throw us out of here. You guys are supposed to be asking questions, or I can get the sound stuff working.
Sounds like work.
Get the sound stuff working? What do you think of question? You got a question?
I don't. I just saying we still have a good portion of time.
Yeah, no,
so,
I would.
yeah.
I'm always trained to cut off at 50 because you're supposed to leave 10 minutes for questions.
Right.
Go ahead.
Where is your office located?
229B in tech, chain technology. Yeah.
So that was, I guess this is where it kind of like relates a lot. So you know how how there's like jammers that are meant to like jam communication.
Right. And in fact, some guy in France just recently got in trouble because he wanted his kids off their cell phones at night after bedtime. So he bought from some gray market site a jammer. And he was a farmer, so he wasn't exactly in a town. But the nearest town, everybody's internet kept dying between like 11 and 5. 11 at night and 5 every morning. And they're going, what the hell is wrong? But anyway, your question.
Honestly, so does that work from constructive or like destructive convergence, or?
What do you mean? Does it work?
I guess is that like how that works? It just in the past, like I thought about like, oh, but I think that would.
Can you have constructive and destructive interference with other kinds of light?
Well, I guess I mean like, does it do either one of those? That how it works? Is it meets like two separate waves? Or, I guess if we're just thinking about.
Well, constructive interference just means you've got wave from two different, whether it's two different points emitting the same stuff at the same time, or the same stuff where one took the direct route and another bounced off something, right? Interference just means you've got two incoming waves that combine. Constructive means that the sum of the two of them is bigger than either on their own.
Yeah.
Destructive means the sum of the two of them is smaller than either on their own, right?
It's like the triangle inequality. We have a thing called triangle.
No, because destructive interference, if you set it up just right, you can make it absolutely zero.
Oh yeah, I've actually seen little videos.
Well, I mean, you saw it today. Exactly halfway between two of those dots, there is no light from this laser.
Yeah.
Right? Now, to you, it looks like pretty well-defined dots. If you drew this light intensity as a function, it turns out it's not that clean, but your eye is logarithmic. If you like cut the intensity in half, your eye goes, not so much. It works on powers of 10, right? So,
What kind of function is it?
I know it better when it's a point. When it's a series of vertical slits, at least in one dimension, it should be an area function. I think. But I'm also so used to doing this in cylindrical radial coordinates that I'm probably not to be trusted on that point.
Cylindrical
If it was a
radial
pinhole through a sheet and I shined a light on it, then it would definitely be an area function at radians. I'm not 100%
No, I just
certain.
wanted to know the name, so.
Well, for a different geometry, that's what an area function is for. Mathematicians say, oh, well, no, it's just interesting. No.
It is an area.
Physicists want it for diffraction. So. That's what math is for. Don't let those mathematicians tell you here. Okay, first do this. So, I'm looking at about, let's see, I'm looking at something like 0.035 seconds of the record. See that there's some bumpiness? Yeah? Further, here, looks like there was a sound, right?
Yeah.
That looks like there was another one. What's going on? Off of sidewalls?
Yeah. Oh. Oh, the bottom.
How do I know that? Because what's the fastest way for sound to first be heard, initial, is
straight down, go straight back up. So the first arrival is gonna be the portion of the sound that did that, right? And if you look at those real closely, you can convince yourself they're about 0.01 seconds apart, right? It's because the sound's gonna go about 3.5 meters. The speed of sound in the air is about 300 meters a second. 343 per second, give or take. Yeah? So, what do you need better than the speed of sound? Something that can sample high enough in a microphone. Yeah? What's the speed of sound in water? Ha!
Lower.
Marine. They don't teach these marine
Ah, you're
people
a marine.
acoustics these days.
No, I'm in math, but I'm taking marine 150.
Oh, you're in marine science class.
Yes.
I thought you meant marine science major.
No, not my field,
Not your gig?
not my cup of tea.
This is just a wave function, right?
No. What this is gonna be is sort of, but that, I would say that that's a little misleading. It's just received sound on that face. This is a function of time. What you're accustomed to calling a
I got
wave
it,
function
I
is
got it.
gonna be some sort of wave amplitude, whether that's a probability wave, an electric field, whatever you want.
It's a Fourier series. I'm just
No.
taking that class. I'm
A
taking
Fourier
I'm
series
taking
would be a
wave.
decomposition of that into different
I'm
frequencies.
taking the wave class.
A Fourier series would be to take this and figure out which frequencies make it up. So the process of
Opposite.
taking a Fourier transform is going from a record in time and asking it, okay, so how much of a 10 hertz signal do you got? How much of a 20 hertz? How much of a 50 hertz?
Okay, what I'm doing is the analysis.
Decomposing it all the way in. An inverse Fourier transform would be to take all those amplitudes at various frequencies and recombine them into a time series.
We are doing both, but currently I'm on Fourier.
This is a time series
Functions
of
of
measurements of sound intensity at that little face. But I'm also
time. I'm
hoping.
sorry if I was just overcutting, I was just curious.
You're gonna ask questions. Thank you, Edward. Is this gonna cooperate? It still thinks I wanna do this one. Just go. There we go.
But in marine science, we are learning about the pings they do off of Antarctica to see the temperature of the water. Is that what you're looking at, like wavelength?
Actually, that's my research. I work on the computational end, but it's long-range transmissions of sound through bodies of water, ocean, very long range, and looking at really tiny discrepancies in the time, travel time, for purposes of extracting the temperature, because if the water's a tiny little bit warmer, the sound arrives a tiny little bit early. The speed sounds a little bit faster, right?
Yep.
So, your crazy uncle on Facebook who says there's no global warming, you wanna see the data? Yeah, I got it. It's a 10-year series in the Northern Pacific where you can see the seasons are like, look like sine wave. The whole sine wave, and if you do it, depends on how you do it, if you do it in travel time, it's down. Right? Because it's getting warmer. But we can only do it for 10 years, despite elaborately designing the experiment so that it could run indefinitely. The sound source isn't even out in the middle of the ocean. It's connected on shore in Kauai and just broadcasts into the ocean. We couldn't keep a continuous record because the increased thermal energy in the ocean after about 10 years changed the current pattern. We wanted our entire transmission path to be in totally dead water, so there was just no other explanation. And for 10 years, there wasn't. And then the California current slid over a little and came into our
global warming, huh? Let's see if this thing is working.
I think my favorite comment on that was, I don't know why, but I ended up taking 2 weather classes, marine now, and I took weather and climate last semester, and can't remember his name for the life of me, but he, the very last chapter we did was on global warming, and he made the point that you can't be a scientist and not believe in global
Absolutely not.
warming.
No, it's not even, when people talk about believing something, they're phrasing it the wrong way. Is it true? Yes.
Is there data?
Yeah.
No, I don't know.
Well, and it's not even, it's more than data in that if you understood the structure of the CO2 molecule and said, we're gonna change it from about, these numbers are rough in my head, 300 parts per million to 400, how much extra energy are you gonna absorb just based on the structure of the atom, the molecule? Well, let's see, CO2 really absorbs super well in the infrared. I wonder what's gonna happen. I could have told you it was gonna happen before it happened, but now it's happened. Let's see. This thing is now working. It's pretty slow because it's trying to send super high. This is an ancient computer.
When did they start that 10-year
La, 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 la,
project?
la, 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 la.
And
What do you
what-
see in the bottom right? Can you see that bar? I don't have my display set up correctly. So bottom right, this guy down here. Speech on a scope. Looks like a bunch of crap, right? It just keeps jostling all over the place, doesn't do anything all that particularly clean, right? All right, stand up for me for a second. And people who can sing can just do that with their voices. I cannot. See? Tone. All right, I'm glad. It was irritating me. The computer wasn't working. More questions? I'm supposed to be encouraging you that science is wonderful and all that.
So like, ask questions. You can sit down, it helps you think.
I ain't gonna sleep on
What made you land on physics? I know this is more personal than science.
No,
in
that's fine.
general.
And in fact, it's always part of when we go to schools, it's important that I have students with me, both because, you know, more relate, but also, my favorite line is, I'm employed, I have to be, you know, diplomatic. They can tell you whatever they want to tell you. But no, it's always part of those events to sort of, hey kids, even if you don't want to go be a science major, go to college, and so on. But for me, there's a winding road. I actually went into college as a math major, but where I went, everybody in the entire college had to take the same 3 semesters of intro physics. The second semester of which convinced me that it was specifically relativity, but that's almost beside the point. That your intuition about the way the world works could be proven wrong. Fascinating. I said, okay, in, you sold me. So I ended up switching to physics from math. But then I'm a complete weirdo. I double majored in philosophy.
Oh,
So
that's
actually
why
applied to
you-
grad schools in both.
That's
I
why you
didn't know.
suggested the Kant book last time.
What's that?
You quoted from Immanuel Kant book last time. I've been reading articles since.
Kant. Even when you disagree with the SOB, he argues so well that you can't just dismiss him ever about anything, even if you don't agree at all. There are some people you can just dismiss because their arguments are horrible. They're silly and rightfully ignored. Ayn Rand. So that was the way it happened for me. But it was also always about, I don't know that I'm the most go-getter guy in terms of, I want to go make my mark in the world and be a success and all that stuff. I just want to know stuff. Physics and philosophy is pretty good pair.
Yeah.
The argument was supposed to be, I may not be able to do anything useful, but I don't want anyone to ever be able to mystify me.
What's your intuition about how world works proven wrong?
Oh yeah, absolutely. And that was what I found interesting, that the way you sort of think, oh, that's the way it must be, but if you could rationally prove that wrong, how do you respond? And I can do it. I can prove that something you think is just incredibly obvious is totally, completely wrong. Right? But in the case of relativity, it's this idea you have, the easiest one to show is about time. This idea you have about time being this universally applicable measurement of the progression of events is just hopeless. It's not even, no, I can prove it's not. Right? Can I do this quickly? Let's see. Guy's in a rocket ship. Guy says, I'm gonna make this is a rocket ship. It's going that way. He's sitting in his rocket ship going, I'm gonna make the stupidest clock you've ever heard of in your life. I'm gonna have a mirror on the bottom and a mirror on the top. I'm gonna have light bounce between the two mirrors. And every hit on this mirror is gonna be a tick of my clock. Yeah? Stupidest clock you ever heard of?
Probably not.
No, it's pretty stupid.
It's
I mean, it's not very practical. You
Yeah.
need something that keeps track of tiny fractions of nanoseconds. Go buy a damn quartz crystal like everybody else. This is a stupid clock.
Okay.
But it's a clock, right? And if you agree that the solutions of the electric and magnetic equations demonstrate the speed of light, then it's just a function of the electrical and magnetic properties of space. Two constants of nature. They're called epsilon zero and mu zero, but whatever. 1 over the square root of the product of those two constants of nature is the speed of light, right? Okay, so everybody has to agree on the speed of light. No problem, right? Why am I worried about this rocket ship dude and his stupid clock? Because if you're sitting there and you say he's moving that way, then according to you, the light is not making this trip, it's making this one. According to you, the path of the light would be longer. So you would say, haha, your clocks are running slow. He would say, no, it's perfectly fine. What are you talking about? Up and down, up and down. What's the matter with you? And he would say, why don't you build a clock just like mine? And you did. You would say his clock's running slow. You know what he'd say about you? Same thing. Because for you, to him, you look like you're going that way. So your light is taking a longer than straight up and down path. He'd say your clock is slow. You'd say his clock is slow. And you're both right.
And both wrong.
No. It's critically important. That's a fundamental misunderstanding of relativity. Somebody's clock is the right one. No. Any reasonably constructed clock is correct.
I was just shitting
It's just
myself.
frame dependent.
I was just shitting myself.
Well, but he should also be able to say what you would think about his clock. Right? It's not like there's any element of subjectivity or randomness to it. It's just frame dependent. If he didn't think your clock was slow, he'd be doing it wrong. And if he said, she thinks my clock is slow by this amount, he can compute how she turns out to do relativity, all he needs algebra. There's not even any calculus in it. It's just madness. But that sort of being fascinated by the fact that no matter how firmly you hold a belief, if it's wrong, it's wrong. As I like to phrase it sometimes, your reason taking your intuition out behind the woodshed.